that the domain would mean that we could only put in positive numbers. But what that problem is saying, by taking the absolute value, is we're actually expanding that out. So if my function is the natural log, I got the absolute value in the right place, right? Okay, so if my function is natural log of absolute value of x, then just thinking about kind of what happens with regular points, well, as long as I'm putting in positive values of x, this is just going to be our regular natural log graph. So it's just going to look like this, going through 1, 0. But now for every single negative x value, like corresponding negative x value, the graph is going to look the same. So this is going to repeat itself over here, because now when I put in -1 for x, this is going to look and take the absolute value of that -1 first, which will be like just saying natural log of 1, and then we'll get 0. So this looks like kind of the graph and its mirror image. I didn't do a great job of making them perfectly symmetrical. They should be perfectly symmetrical, but it's basically your regular LN graph and the mirror image. Now, an interesting one that he didn't ask you to do, but what happens if we put the absolute value on the outside? Yeah, and so what's going to happen, like graphically, is that we would kind of start with that natural log graph. Scoot up, yeah. But any of the, we'd kind of start with a natural log graph shape. But this portion down here, where the y values would be negative, get flipped up and become positive because of that absolute value. So this one actually looks really weird and kind of does this.
So it's like bouncing.
Yeah, it's like we're taking this part of it and flipping it up. Yeah, I know you weren't asked to do that. I just figured we could take a look at another example. Other requests for any of these specific problems, or I can make up more examples kind of in any of these general areas from homework 3. So we've got graphing, we've got applying the inverse property, which really just means simplify these things as much as you can using the properties of logs and exponential functions. We did some expanding the other day. Happy to do more of that. What are y'all in the mood for? Can we do number 3? Heck yeah, we can do number 3. So looking at number 3, a couple of them here. I know that there are not parentheses around this stuff, but it's implied parentheses. It's natural log of this whole mess. And I know that's not on the screen. Bear with me for a second. So that's, it's not terrible. So the instructions here are to expand this. So this is where we're using all of those properties of logs. When I kind of take a step back on this whole thing, overall, I've got this big division thing happening. So when we spread that out, that's going to become ln of x plus y. minus ln square root of x cubed plus 1. And let me try. With that. Okay. But we can keep going more because that square root, if we think about that as really saying we have stuff to the 1/2 power, then that exponent can come down in front. Now, usually, right, the whole reason that we're practicing expanding this stuff out is because it makes it easier to take the derivative. This homework didn't ask us to do that, but that's kind of why we're practicing this skill right now. Let's take a look at that second one. And the second one, I've got natural log, the absolute value of x times the cube root of x squared minus 1. Now, as I was reading that, I said something critical here, which is there's an implied multiplication between the x and the cube root of the garbage, which means when we expand that out, we'll have ln of x plus ln of the cube root of x squared minus 1. And then similar to what we did with the square root, I can rewrite that as a 1/3 ln x squared minus 1. Now, I would argue that we should probably keep going because x squared minus 1 factors. And since that factors, if I were going to fully expand this, I would want to treat that as ln of x plus 1 plus ln of x minus 1. And then you can distribute the 1/3 in if you want or not. Good times. There's a request in the chat to take a look at problem 2 also. Totally happy to do that. And just like as a quick refresher, if I take the natural log of e to the x, I get x, which means natural log of e to some stuff is the stuff. And if I take a look at that similar statement, but sort of in reverse. Hold on, there we go. But if I take a look at that similar statement, but in reverse, like thinking about it with exponentials, e to the natural log of x is equal to x, or e to the natural log of some junk is equal to the junk. And that's what is meant by the inverse properties. So when I take a look at some of these on problem number 2, natural log of e to the x cubed, that whole x cubed piece is our stuff. So e to the natural log of x cubed is just going to spit out x cubed. I'm adding parentheses in here that aren't like explicitly in the problem, but for me, it really helps to kind of see how things separate out. If I look at e to the natural log of x minus 2, again here, that x minus 2 is sitting kind of like the junk. So e to the ln of x minus 2. is x minus 2. E to the ln e to x. Well, this guy I didn't add any parentheses to, but I'm gonna stick some in right here, because this kind of generally has that form that looks like, sorry?
No, I'm saying like, it
Yeah.
looks like the second one.
Yeah, exactly. It looks like the second one, which means it's just gonna spit out e raised to the 2x. And there isn't a way to simplify that. We're done. That's as far as we get. Like scale of 1 to 10. If you had a quiz on this stuff, like just the manipulating log, scale of 1 to 10, like what score would you be getting out of 10? If you're on Zoom, you can type it in the chat. You can type it privately in the chat. Are we like 2 hands? 1 hand? Like where are we at? Okay. No one on Zoom is buying into my typing numbers in the chat. It's okay. I got a couple. Maybe like a 7. Since I'm not seeing like a whole ton of 10s, let me make up just a couple more examples in this area, and then we can talk about something else. So let me just give you one to try on your paper. And I'm just going to aim for a simplified kind of problem. How about and let me give you one more here. I think I made both of mine more complicated than the ones you had on the homework. So I'm going to give you a minute or two to mess around with them. Should I come save us? Should we check them out together? So taking a look at the first one, we've got ln of e to some stuff. So the stuff that we're going to get is 4 natural log of x, but this, I would argue, can be simplified more, maybe, or at least another form of it would be what? Ln of, right. I don't know which one of those looks simpler. I don't know which one, depending on the situation, we might want to choose one or another. This second one is a little bit trickier because it doesn't perfectly fit in with the e to the ln of some junk. I threw us off by putting that -2 in front. So before we can apply that inverse property, we actually have to take that -2 and stick it back in as an exponent. So I would have to write this as e to the ln of x cubed raised to the -2. And now I can move on. Now my e to the ln, that inverse property is going to leave me with x cubed raised to the -2, but powers raised to powers will make that an x to the -6. And I asked on Zoom, but I didn't actually ask in class. So I know you all did interest rate kinds of problems and compound interest stuff. Did you all talk about exponential growth and decay or half-life, radioactive stuff? No? Okay. Cool. Yeah.
And like the test, did you say they would for the first problem, would they accept both?
They would accept both answers. Yeah, for sure. Yep. And so should we keep cruising through some of these homework problems? Should we bounce back to talking about derivatives? Should we talk about exponential growth and decay and half-life and all that good stuff? Since it's one of the applications of exponential functions that is in section or in chapter 4. I'm open to anything. Do we want more practice with derivatives or more practice with applications? Applications, okay. So my guess is that in somewhere in a biology class, in a chemistry class, in some previous life, you have been introduced to the idea of radioactive decay and half-life and those kinds of things. Now, secretly, our equation for exponential growth or decay is the same as our equation for continuously compounded interest. Good times, right? So when we're talking about radioactivity or exponential, I'll move it in a second, exponential growth or decay, the overall equation that we're usually working with is something like y equals CE to the KT. So if I started with, let's do some exponential growth. So let's say that I started out with 200 cells in my experiment. And after 3 hours, now let's make it 8 hours. After 8 hours, there are, I'll make the numbers nice on this first one and then we'll make them messy on the next one. There are 400 cells. How long will it take to have 1,000 cells? Assuming exponential growth. There's usually going to have to be some sort of clue in the problem that lets us know that we're talking about exponential growth or decay. If the word radioactivity or half-life shows up, then we already know we ought to be in this realm. Typically, if we're talking about exponential growth, we kind of have to be told that it's exponential growth. So anytime I'm talking about exponential growth and decay, and I'm looking at this equation, y equals ce to the kt. Okay, that's 5 letters. Of those 5 letters, how many of them are constants? So thinking about like, there are 5 letters up there. I would argue that 2 of them we usually label as variables. And 3 of them are secretly constants. So, oh, you were trying to give me an answer already? Because you were like doing cool things in your head? Oh, no, that's okay. I wasn't doing cool things in my head. I was just going back to our equation over here. So E is a constant. E is the like 2.71828 thing. But C and K are both constants that are particular to the exponential growth situation or the exponential decay situation. So our starting point is almost always that we've got to figure out those 2 constants. If I have 2 constants to solve for, I must have been given 2 pieces of information in the problem. And that's my starting point for any of these. So if I'm looking for 2 pieces of information, well, one of them, I've got these 200 cells. And at the start, that's secretly telling me that when t is equal to 0, y is equal to 200. The other piece of information that we were given here is that after 8 hours, there are 400 cells. So when t is equal to 800, my y value, I don't know why I wrote 800. I had like 100 in my head. I'll just blame it on Friday. So we'll just get rid of those. Yeah, good times. So when t equals 8, y is equal to 400. These 2 things are going to allow me to solve for the c and the k value. My guess is, if you've done this before, some of you probably remember that c is just our initial value. But we can get there in case you forgot that part. Anytime I've got a 0 for one of these things, I'm definitely using the 0. So if I start with this, with the 0 one, then this looks like 200 is equal to ce to the k times 0. But e to the 0 is 1, which means that the c value, the value of that constant, is 200. Now that I know that, I can use the second point. I've got that 400. I'll replace the c with 200 now. And then we have e to the k times 8. So go ahead and solve for k on your paper. And simplify along the way if you can. But get it down to saying like k equals something. Did you all talk about derivatives on Wednesday? Derivatives of log functions in lecture? Okay, I was just checking to see if he's like still on target. So looks like the answer is yes. Cool. Did anyone get a value for K? Even if it's messy?
I'm fine.
Do we get to a place where we're stuck?
I'm stuck like getting to the exploring.
Yeah, totally. So let's deal with that exponent. So for sure I can divide both sides by 200, and I'm going to go ahead and simplify that and just say 2 is equal to e to the 8k. Well, now we have a choice. We can think about, like, go back to thinking about our properties of logs. And my old friend, log base 2 of 8 is equal to 3 because 2 to the third is equal to 8. Or we can exploit the inverse property of logs and exponentials like we were just practicing. And that ends up being most of the time our faster option. So similarly to being able to like divide both sides of an equation by the same number or add or subtract the same thing to both sides, I can log both sides of the equation and not change the equation. So I'm going to sweep in here and do natural log of 2 is equal to natural log of e to the 8k, and then use that inverse property that tells me this side is just 8k. And if ln of 2 is equal to 8k, then k must be ln of 2 divided by 8. And there's not much we can do with that short of like shove it in a calculator, right? I don't know what the natural log of 2 is. We're kind of stuck there. Just notation wise, and like if you're watching someone else do this, another way that we can go from here to here is to use the log property that says that 8k is an exponent and can pop down in front. And then the natural log of e is equal to 1. What you don't need to write out this intermediate step unless you personally need to write out this intermediate step. You could go straight from this line to natural log of 2 is equal to 8k. And you'll probably see that like if your TA was writing up solutions or something, probably going to skip that intermediate step. Okay, we got our constants, but we didn't actually answer the dang question. The question is, how long will it take to have 1,000 cells? Well, how long is secretly asking me for a time. So we're looking for what's the time when y is 1,000. Now I made the numbers nice, which is why you can do it in your head, but let's work through the mathy version of solving for that. Because if the problems don't have nice numbers, we're going to have to use math. So if t is equal to 1,000, we know what the value of k is. We know what the value of c is. So I'm going to go back to our y equals c e to the kt. I'm just going to plug in our values. So c was 200. K is natural log of 2 over 8. So I'm going to have ln of 2 divided by 8 times t. And now we can plug in the 1,000 for y. So I've got 1,000 is equal to 200 times e to the ln 2 over 8 times t. Well, 1,000 divided by 200, that I can handle. That's going to give me 5 is equal to e to the ln of 2 divided by 8 times t. Well, that looks gross. We have options. We can either work with the right-hand side and try to deal with the inverse property of E and ln by manipulating this, or we can just sweep in and take the natural log of both sides again. I think it's easier to just sweep in and take the natural log of both sides again. So I'm going to have natural log of 5. And this time I'm going to skip writing out that intermediate step. So when I take the natural log on this side, that exponential part's going to go away. So I'll have ln of 5 is equal to ln of 2 divided by 8 times t. And if I have to get the t by itself, kind of have a couple options here. I'm going to take the lazy approach first, which is to just divide both sides by all that garbage. And since you don't get a calculator on a test, right? Did anyone ask? Usually you don't. No, then that's where I'm going to leave my answer. Maybe that's something pretty, maybe it's not, but I'm going to leave it there. We do a radioactive decay one. I'm leaving this for a second in case there are questions. I'm not seeing questions on Zoom. Not seeing questions in the room. Good times. It has been a long time since I took a chemistry class, so I'm gonna make up my own element. It is not real. My mythical element is going to be called lolonium. I don't think that's really an element. Unless things have changed a lot on the periodic table. Pretty sure that's not an element. So got lolonium, and lolonium has a fake half-life of 480 years. My fake element. So here's the situation. We have a sample of 10 grams of lolonium. How long will it take for 2 grams of our sample to decay? Good times. Since we've got the word half-life in there and we're talking about exponential growth or decay, I can already know that we're working with y equals CE to the KT. I want to talk for a second about this phrase half-life in particular. So right now we have a sample of 10 grams. And what it means to have a half-life of 480 years is that we would decay to 5 grams, meaning we'd be at half the mass after 480 years. So if I think about like the time and the Y value, so right now we're at 10 grams, sorry. Now we're at 10 grams, and in 480 years, we'd be at 5 grams. And why did I give myself 480? Okay, so 480 times 2, that's 960. So in 960 years, I'd be down to 2.5 grams. Because each time we're taking half of the previous mass. Well, this idea of half-life actually secretly gives us the value of K in our formula. I'm going to do it kind of generally, like derive what's happening generally in terms of that half-life. So sometime, well, I don't know, I'm gonna use like THL for half-life. So if C is our initial amount, then when my time reaches the half-life, my Y value should be half of C. If I stick that in and I replace my Y value with 1/2 C, and I replace my time with this thing that I'm calling T half-life, then we can actually solve for K and have like a generic formula for this. So I can divide both sides by C. And I'll have 1/2 is equal to E to the K times T half-life. And then use the same trick that we used on the previous problem. I'm going to sweep in and take the natural log of both sides to get rid of that E. So I'll have natural log of 1/2 is equal to K times T half-life, which means that T, or sorry, I was trying to solve for K. That's a K. So my K is equal to ln of 1/2 divided by T half-life. Now there's another version of this formula that comes from thinking about properties of logs. So this is just sort of like my little aside up here, but natural log of 1/2, if we used our log properties, I could expand that to say natural log of 1 minus natural log of 2. But natural log of 1 is 0. So the other version of this formula looks like K is equal to negative ln 2 divided by T half-life. I will be honest, I don't remember which one the book gives, but I think it's this one. Not with the 1/2 in it, which I think is too bad because I think this is easier to remember because then I'm like thinking about halves because it is half-life. They'll give you the same numerical answer. It doesn't matter which one of these two you choose to use. So let's zoom back into our problem. So based on what we were given, we have an initial amount of 10 grams. So we know the value of C. And we can use this formula to know our value of K. So for our problem, C is equal to 10 grams and K is equal to ln of 1/2 divided by 480, or negative ln of 2 over 480. And the question I asked was how long for the sample, how long for 2 grams of our sample to decay? So one other thing to be careful of in our equation is that Y is telling us the current amount that we have. So if 2 grams have decayed, we actually have 8 grams left. So the question I'm asking is, what's the time when Y equals 8? Plugging all of that in, I'm looking at 8 is equal to our C of 10 times E to the messy K value. I'm going to go with this one. Oops, ln of 2 over 480 times time. And since I rearranged the last one for us, I'm going to let you all solve for time on your own this time. And remember, it's okay to leave it messy. You can leave it really messy. Decimals or fractions? Does anyone have a preference? Fractions? Okay. So 8 divided by 10, I could simplify to 4/5. I'm just going to write that as e to the stuff for now. And then I'll take the ln of both sides. And I'll have ln of 4/5 is equal to negative ln 2 over 480 times t. Man, that's gross. Which means t is equal to ln of 4/5 divided by negative ln 2 over 480. Gross, but given time, energy, sufficient monetary motivation, and a calculator, you could turn that into a number, right? Should we turn it into a number? No thanks. No, we're good. Okay. Okay. That's fine. We have about 5 minutes left. Should we practice a few quick derivatives? Just keep that part fresh. And for those on Zoom, I am keeping an eye on the chat. I just haven't seen questions popping up there yet. But let me go with, how about y equals natural log of 3x cubed plus 4x. And what I actually want to find is, let's find the equation of the line tangent to the graph
The graph of the curve.
when x equals 1. Well, if I graphed it, it would be a curve. It's Friday afternoon. Should I do this or did you want to mess with it for a minute? Yeah, go for it. We're gonna need some chain rule for sure. And if it's been a minute since you found the equation of a tangent line, I will at least refresh your memory that this is usually the easier form to put stuff into for calc. Because we are almost out of time class-wise, I am gonna zoom in and at least like finish this problem. I love partial credit. So if I looked at this problem and I didn't know how to take the derivative, I would at least start by saying, cool, I know I'm supposed to plug in 1 for x. And if I plug 1 in for x, 1 cubed, it's 3, it's ln of 7. Partial credit, bam. Now, also, maybe you looked at this problem and you were like, I know I'm supposed to take a derivative of something. Maybe you know the derivative. Well, the derivative of natural log of some stuff is 1 over that stuff times that chain rule part where we take the derivative of the inside. So I'm looking at 9x squared plus 4. And in particular, my slope is going to come from that derivative after we plug in 1 for x. So if I plug in 1 for x, 9 plus 4, I'll get 13 on top. And I think I'll get a 3 plus 4 on the bottom. So my slope would be 13 over 7. And my final answer would look like y minus natural log of 7 is equal to 13/7 times x minus 1. And I would quit there. Just a couple quick reminders. I do have office hours on Zoom today from 2 to 3. Also, drop-in tutoring over in Shields Library starts this weekend. So starts on Sunday from 3 to 7. And then on Monday during the week, they're open from 11 to 4. If I don't see you this afternoon, I hope everybody has a super lovely weekend.